So great to see you back in the One World Signal Processing Seminar series. Today we are featuring a talk by Christoph Studer from ETH Zurich, and I would just like to briefly introduce our speaker of today. Professor Studer received his master and PhD degrees from the Department of Information Technology and Electrical Engineering at ETH Zurich. He was a postdoctoral researcher at ETH Zurich and Rice University, and from 2014 to 2020, he was a professor at Cornell University in New York. Since 2020, he's an associate professor in integrated information processing at ETH Zurich, and his research and teaching activities are in the area of digital integrated circuit design, wireless communications, digital signal processing, optimization, and machine learning. Today, he will speak about low resolution to the rescue of all digital massive MIMO. So I would like to hand over to you, Christoph. Yeah.
Okay.
So the floor is yours.
Yeah, thanks a lot, Marius, for the introduction. Let's hope this will all go well. I will talk about today on how we can use low resolution analog to digital converters and digital to analog converters, as well as low resolution signal processing to make massive MIMO receivers and transmitters way more efficient. And let me just start with some things that probably most of you already know very well. Multiple input, multiple output, or short MIMO is widely used in most communication standards. The idea is you have multiple transmit antennas and multiple receive antennas, and you can send different data from different antennas, which get mixed in the air, and then hopefully the receiver can undo this mixture to recover the individual data streams. And this basically improves throughput and also coverage at theoretically no expense in transmit power, and that's also why it is widely used in communication standards. However, conventional small-scale point-to-point and multi-user systems, they already reach their limits in terms of system throughput, so of course we're searching for newer technologies. And if we think about what's happening after 5G, in principle, we would like to combine two technologies. One is massive multi-user MIMO, which is already widely used. The idea is to have a base station and you equip it with multiple antennas. For example, we call it B in our talk. And then we have a large number of antennas, and with this we can do fine-grained beamforming, so we can focus the energy towards the users, which leads to an array gain. And then also we can serve multiple users at the same time by pointing different beams at the same time to different users. And the number of users in this talk is and we will use that fairly often in what follows. The second technology we would like to use is millimeter wave, and the reason is because we have a huge amount of contiguous bandwidth available there. For example, if you go slightly above 60 gigahertz, we already have 2 gigahertz of bandwidth that we can use. The problem at these high frequencies is that we have to combat atmospheric absorption, so we typically end up with receiving almost no energy. So we have to do beamforming, which is very good because for massive MIMO we will do beamforming anyway, so this comes very naturally. So another thing that is maybe not that popular yet is the idea of using all digital base stations. There's a lot of research around hybrid base stations, but I will focus on all digital base stations. And the difference is that for all digital solutions, that each antenna basically has a pair of ADCs and a pair of DACs. So basically for the received signal I and Q, you have two ADCs. For the transmit signal, you have two DACs, and each antenna would have one of them. And the reason why this is particularly attractive is it allows maximum flexibility for beam and null forming, but it also simplifies many of the critical baseband processing tasks. For example, synchronization, channel estimation in particular is trivial compared to hybrid systems. Beam finding and tracking is also easier, equalization is easier, precoding is easier, and so forth. Then another important advantage is that the RF component, the number of RF components that you need is minimized. So the circuit design effort on the analog side is reduced, which is also important because typically this is something that needs quite a big engineering teams to do well. And then another advantage of all digital architecture is because we minimize the amount of RF components. If we want to migrate our design, we can migrate everything that has been done in digital, which is maximal here. So there's minimized the amount of work that is done in analog. So we can easily go from one semiconductor technology to the other, whereas only the analog components would need to be redesigned by hand for the next technology. So this is another very important advantage. So now, if we think about using all digital massive MIMO, we would have hundreds of base station antennas. Of course, we have to process high dimensional data. if we think about millimeter wave communication, where we try to use gigahertz of bandwidth at the same time, we would have to solve billions of tasks per second at high dimensions. Then also getting this data from all the ADCs into a chip and also through interconnect will result in very high data rates. And then on top of that, we have to process this high dimensional and high bandwidth data in some processing fabric at extreme throughputs. So if you think about this, it's actually extremely challenging. And in particular, I would like to emphasize that it's impossible to just take solutions that we've done for small scale MIMO and just scale them up to more antennas and more bandwidth without being careful and without developing new technologies. Okay, so maybe also another motivation fact is this: if you look at the RF power consumption of high quality RF chains, so we have one for the uplink and one for the downlink. This is for a picocell. And if you look at the power breakdown here, you can see that ADCs and amplifiers uses about half of the power in the uplink. And in the downlink, of course, the power amplifier requires way more. Compared to a low noise amplifier, it's about almost 3/4 of the power consumed by ADCs and DACs and power amplifiers. So as you can see data conversion amplification consumes a large amount of power. And of course, the idea would be to somehow reduce this power consumption. And what I'm going to do in this presentation is to show that massive MIMO enables us to do reliable communication with low resolution data converters, and also that we can not just convert the data into low resolution, we can also do the signal processing at much lower resolution in the hardware later. So everything today is going to be about ADCs and DACs, but also about low precision processing. So why is low resolution important? Maybe you want to ask this question. And the idea here is that if we lower the resolution of data conversion, then basically we can reduce the power consumption at each ADC and DAC. And this is extremely useful because in a massive MIMO system, of course, the number of ADCs and DACs is very large. And in particular, if we focus on all digital systems, the number of ADCs and DACs is really the number of antennas, basically times 2. Then if we lower the resolution, then we can also simplify the remaining RF circuitry. So the RF circuitry before or after the before the ADC or after the DAC, we can also reduce the complexity and also the power consumption because they only have to operate at a precision or resolution or linearity that is just above the quantization noise floor. And then also another interesting aspect that has quite been overlooked in the past is that even the subsequent digital processing can also operate at low resolution, but I will talk about these two things. And then another advantage is that by reducing the precision in the ADCs, we can really reduce the data rates, which is an extremely important aspect. Because if you think about a system with 256 antennas and 10 bits in ADCs at each antenna, sampling, say, at 200 megasamples per second, that already requires a 1 terabit per second link, which is actually very difficult to implement already. And this is not necessarily the largest 200 megasamples per second is not really what you would like to do. At millimeter wave, you potentially would like to go like 10x or even more higher than that. Okay, so briefly what I'm going to talk about is how we can use low resolution ADCs in the uplink. So when the users communicate with the base station, low resolution DACs in the downlink. So when the base station communicates with the users, and then also how we can use low resolution processing to further reduce the power consumption. So again, let's focus just on the uplink. So as I said, users send data to the base station, and I will do a little bit of mathematical modeling, but then try to keep the math as little as possible. So the system is as follows. We have on the left side multiple single antenna user equipments. In the middle here, we have a all digital base station with LNAs, mixers, and ADCs. And imagine we have ADCs that convert the real and imaginary part or in phase and quadrature part with 1 bit each. We basically get 4 points that go into the digital processing on this side. If we would have 3 bits per ADC, we would have these 64 points here that we would have available for processing subsequent for channel estimation and data detection, for example. So let us model this system, and we are focusing on a frequency flat system. And you will see, I will talk very briefly about the frequency selective case, but this one here just for simplicity. So we have S, which is the vector of the transmitted user data. So each entry of the vector S contains, for example, 16 QAM symbols. We have H, which is the MIMO channel matrix. We have additive noise. In this case, we model it as Gaussian. And then we have this operation, which is a quantizer, which acts element-wise on the vectors. And then we receive the quantized symbol here in the vector Y. So this is the model we're going to use. So how do we model quantization errors, or how can we deal with that? There are basically multiple ways. The simplest way is to assume that the input is some kind of a zero mean Gaussian random variable, and we decompose the output of the quantizer as just the input itself plus a statistically dependent quantization noise Q. And the problem with this is an approximate model because first the quantization is statistically dependent on Y, and also it's not that easy because the statistics of Q are difficult to deal with. So this is not a particularly good model. Another approach to model a quantizer like this is to model the whole process just as a probability distribution. So you assume you know the input distribution, and then you can model what is the probability of observing the outputs. This model is exact, so there's no approximation here, but theoretical analysis is difficult, but also developing algorithms for this model is not very easy in practice. A very popular way of dealing with quantization errors that has emerged maybe in the last 10 years is Bousquin's theorem. If you've never heard of it, you should definitely read about it. The idea is that you basically use a similar model as the additive quantization noise model, but you allow a gain to your input signal. So instead of just taking the input signal directly, you allow here a gain. This gain factor is typically smaller than 1, so between 0 and 1. And then a uncorrelated quantization error E. And the gain factor here is chosen so that the quantization error is uncorrelated with Y. So in the previous model what I was showing, there will actually be statistically dependent and correlated. You can actually decorrelate them with this, and you can see this as kind of a first order statistical independence, and that is very useful for a theoretical analysis in practice. And as I mentioned before, this tool is actually well known, especially for RF designers. For many, many years, they were using this to analyze, say, RF chains, but only about in the last 10 years, it has been used in digital signal processing, and especially in the massive MIMO community. And it is very well known for those who know, and if you have never heard of it, you should definitely read about it. It's an extremely useful tool. Okay, so if we use this Bousquin's theorem, we can basically take our system model that we had before and we can linearize it. And the linearization is really just that you have, instead of the quantization function of what we receive here, we have now a matrix G that is diagonal, and the diagonal elements are governed by the quantizer resolution and also the statistics of the input. But again, the interesting part is here that we have the quantization error is now uncorrelated with basically S and N in this system here. And with this uncorrelatedness, we can easily derive a linear channel estimator, and this is shown here. It's not really important that you know the details how this works, but basically the point is that if you have a linear system, of course, you can devise a linear estimator where the estimator depends on the Bousquin gain, of course, the number of pilots, and also the SNR. And as soon as we have an estimator, we can then just do zero forcing equalization. So we can take then the quantized received signal, again, observed through the same linearized model, and then we can create an estimate of the transmitted signal. And the question is whether such simple methods like linear channel estimation and linear receivers work well with coarse quantization. And it turns out that it works extremely well. So this one here is a 1-bit system. We assume QPSK transmission, Rayleigh fading, 210 us 10 user equipments and 10 pilots. The markers correspond to simulation results, so Monte Carlo simulations, and the solid lines are theoretical analysis of the bit error rate. And you can see that we are extremely accurate by using this Bousquin decomposition, despite the fact that 1-bit quantization is extremely nonlinear process. If we increase the resolution to say 2-bit, per in-phase and quadrature component, you can see again, theory matches extremely well the simulations, but also we get significant improvements compared to the 1-bit case. And if you go to 3 bits, again, we get some improvement, but what is most importantly with 3 bits, we're almost extremely close to the infinite resolution case, which basically means there's an absence of any ABC in this case. So 3 bits in this case, you can see, even with very simple linear receivers in a massive MIMO scenario, is completely sufficient. Again, you may think, oh, this is all frequency flat, it's super trivial. We have plenty of results for wideband systems, and I'm skipping these because otherwise it will take too much time. But basically everything I was showing before, you can use Bousquin, you can use algorithms to do that. You can implement these algorithms. You can also do for multi-user MIMO OFDM systems, but I'm really going to skip this. So you basically have to believe me that this is true. Yeah. But what I would like to do now, we know that in the uplink, we don't need that many resolution of bits to get good performance. The question is now, what about the downlink? And the downlink, again, to do that, let's model the downlink. And the downlink is slightly different because there's a presence of a precoder, which I'm going to explain. But on the left side, we have our base station, our massive MIMO base station. On the right side, we have U users. And the base station consists of the data that we want to send to the individual users, a precoder, and then we have an array of DACs, mixers, power amplifiers going through the channel, and then ends up at the single antenna, user equipment. Again, we're focusing on a frequency flat system, and the system now is modeled from the output of the DACs to the receivers, to each antenna of the user. So this vector Y contains all the received symbol at each user. So the first entry, for example, of this vector would be the symbol received at the first user. Then H again models the channel matrix. This is now the downlink channel matrix. And then X is what's coming out of the DACs. And the vector X is a function of S, which is the data we want to send to the users, and also knowledge of the channel state. And basically there is a mapping. There's a mapping from symbols to there's a map from symbols to the channel vector H to what we actually want to see at the output of the DAC. So the vector X is a discretized vector that has the resolution of the DACs that we have. Of course, we have a power constraint, and then basically the idea is that after this vector X passes through the channel, we would like that the users see the symbols they deserve to receive. Okay, so the goal of what we have to do, we want to find the output of the DACs, where the outputs are picked from this discrete constellation, where B is the number of base station antennas. And what we would like to do is we would like that the received signal on the received side, we want to minimize the mean squared error between what we actually want to send to the users and what the users receive. And the way we do this, we make sure that the users are able to scale up, or basically do a very simple scalar equalization step to what they receive. So basically we have S hat, which is the user's estimate, minus S, what we want to send. And we want to minimize the mean squared error averaged over noise, over the noise realization. So this can be decomposed in this specific way. And then what we can do is we can formulate a MSE optimized quantized precoding problem, where we want to minimize this MSE. We want to find the outputs of the DACs. So what should be the discrete outputs of the DACs, and also what should be the equalization values for each user, subject to the power constraint that we impose. So we would like to solve this problem. The interesting thing about this problem is, because of the discrete nature of X, of the vector X, this is an empty hard problem, because it's basically a closest vector problem with some regularization. And if you think about solving this, for example, if you have 256 base station antennas with 1-bit DACs, if you would do an exhaustive search on this problem, you would have to evaluate the objective function more than 10 to 154 times. So you can imagine this will never work. So clearly we need efficient methods and approximate methods to implement this approach here. The simplest method that you can think of is just what we call linear quantized precoding. Basically what you do is you ignore the presence of a quantizer, you just apply a linear precoder. And then after the linear precoder, you quantize the output of this precoder. And the way this works, really, we take our transmit vectors, so the symbols we actually want to send to the user, we multiply it with the precoding matrix P, and then we quantize. So this is like really the most trivial thing that you can think of a quantized precoder. And then the good thing again is we can analyze such quantizers using Buscang's decomposition. You've seen this before, and we can do similar curves, bit error rate versus SNR curves that you've seen before. And again, we have simulated our markers, solid analytical results. And again, you see for 1-bit DACs, in this case here, the performance is not that great, but if we increase to 2 to 3-bit, if we're at 3-bit, we're already very close to infinite resolution, which is again, the absence of any DACs in this case. So the key question is now here, what you may ask yourself, so how close are these methods to optimal performance, especially for low resolution? We know for high resolution, we're very close, but what about if we have, say, 1-bit DACs, how close are we to optimal performance? And we can basically answer this question by taking a very small problem for which we can do an exhaustive search. And that's what we do here. We pick 8 transmit antennas and 2 users, and we pick 8 transmit antennas because we would like to do an exhaustive search. This is 1-bit signaling, and this is assumed at infinite SNR so that we don't see the effect of noise. And then this on the left side is the received constellation for 0 forcing with 10-bit DACs. And you can see basically you get a perfect received constellation. But if we do 0 forcing followed by quantization, which was this very simple approach. You can see basically we receive a complete mess, and you can imagine the performance is really bad. Now, if we solve this quantized precoding problem that I was mentioning before, the NP-hard problem, you can see we can do significantly better in this case. So there's a big gap between linear quantized and non-linear, or this exhaustive search method. And the question, of course, is, can we design algorithms that go closer to what we see on the right than what we have in the center without having too high of complexity? And the solution to this is what we call nonlinear precoding. Basically, it's a function, it's a nonlinear function that takes in the transmit symbols, information about the channel, the noise variance, and generates the DAX output. And we would like to solve this problem here that we had before. But of course, we would not like to solve it exhaustively. We would like to solve it using approximate techniques. And basically, there are two prominent alternatives. One is semi-definite relaxation, which works extremely well if you have 1-bit DAX. And then another thing is that we developed is what we call this biconvex 1-bit precoding, or C1PO, is another heuristic to solve this method efficiently. And if you look at the performance, so this is another plot where we have the bit error rate versus the SNR. The black curve is the infinite resolution case. The blue curve here with the square results is 1-bit zero forcing. And then the two methods that I was just mentioning, semi-definite relaxation and C1PO, basically get about 2 or 3 dB close to infinite precision. Remember, this is for 1-bit DAX in this case. So there's a significant gap that you can close by using sophisticated algorithm. And the interesting thing is also the complexity of these methods is not too extreme, especially the complexity of C1PO. Semi-definite relaxation is very difficult to implement in hardware because typically you solve an interior point method, which requires quite a high arithmetic precision. But C1PO, our algorithm, was developed with a hardware implementation in mind. And this is actually a chip we have designed that you can see on the bottom here in this square box. Underneath this box, there's actually a 1-bit precoder for a 32 antenna system, which can precode about 20 million vectors per second. And the power consumption is also in the milliwatt regime. So clearly this can be done efficiently in practice, and you don't need any huge hardware expenses to do this. And you can do significantly better than linear precoder. So this is just to demonstrate that these methods actually work in practice. Okay, so this was just, again, to show that we can do uplink low resolution, downlink we can do low resolution, but now comes something that is a little bit different to what the mainstream research is can we also do the processing later in digital? Can we do this at low resolution as well? And again, to analyze that, we focus on the uplink just to make it simple, but this time we're also interested in millimeter wave, where it's actually really important to minimize power consumption. So again, we're looking at a system where we have multiple users. We have a base station with B receivers, and we have a channel estimator and a spatial equalizer. And again, we consider a frequency flat channel, but of course, everything can be extended to wideband or frequency selective channels as well. So there's nothing really different here, so I'm going to skip the details, but basically our goal is we observe Y and have knowledge of the channel or an estimate of the channel, and we would like to recover S, and we would like to do this task in as little power consumption as possible. So if you look at the baseband processing itself, so we have our RF and our ADCs, but then what do we need to do? So the simplest baseband processing is this spatial equalization task, which we can do in a linear fashion. So we take a received vector. So the received vector is the output of the ADCs here. We multiply it with a matrix, and the output of this matrix will be our estimated symbol. So this would be the simplest that you can do. This is known as linear equalization or linear spatial equalization. And the problem in these systems, the spatial equalization task has to be done roughly at the ADC sampling rate. So it's really proportional to the bandwidth that you would like to work with. And the goal is to suppress multi-user interference and also to reduce basically the data to go from B observations from B-dimensional vector to only U vectors in this case. And if you just naively implement such an equalizer, so you implement a matrix vector product in hardware, for example, in 28 nanometer CMOS, and you would like to support 1 gigahertz of bandwidth, then a naive implementation for a 256 base station system would require slightly below 30 square millimeters. For those who don't really know how much that is a lot. And then also about 21 watts just for this task of this matrix multiplication. That ignores all the other tasks that you would have to do in the base station. And that is actually quite significant in this case. But the point is, what I would like to show is, before we were only focusing on minimizing the resolution of ADCs and DACs, but you can also reduce the resolution of the processing. And the motivation behind this is that if you do a multiplication between two numbers, the complexity of the multiplication does depend on the resolution, of course, of both operands. And in particular, a hardware multiplier, the area roughly scales with the number of bits of the two operands. So if you have an m-bit operand and an n-bit operand, the area roughly scales with the product of the two, and the delay, so the time it takes to do this multiplication, is roughly the larger of the two operands, the maximum in the logarithm. So this is a rough approximation. And then also you can think of that the power consumption is roughly proportional to the area of the multiplier. So never quote me on this, even though it's actually fairly accurate in many cases. And you can see, so now if one operand is the received vector, which we already quantized, you can imagine that if we can also reduce the weights of the equalization matrix, which would be the other operand in our multiplications, then we can significantly reduce area, delay, and also power consumption. So this is exactly what we would like to do. Let's reduce the precision of the equalization matrix in our case. And a trivial or naive approach is you just calculate your, say, MMSE or linear MMSE equalization matrix, and then you quantize each row, for example, to binary values, say to minus beta and plus beta, where beta is some optimally chosen value. So just think about it, just an antipodal quantization of each row independently, and each row can have a different scaling. And then the interesting thing is that a multiplication with such a binarized matrix requires only addition and subtraction, so we can completely avoid hardware multipliers, which is significantly more efficient than, as I said, that using multipliers in this case. So addition is like significantly simpler in hardware. So let's see how well that would work. So this is now a result for the naive approach. We have, again, SNR versus bit array. This is now coded, just that you can see we can also deal with coded systems. We have 256 antennas. We have 16 users. The users are transmitting 16 QAM. We use a millimeter wave channel model in this case. This is now also using OFDM, so I'm skipping many details, but basically this is to show what we can do. And now the interesting part is if we quantize just the weights of the LMMSE matrix, you get a significant performance loss. You can see here it's about 6 or even more dB loss at about 1% bit error rate. So clearly this is probably not the right way, just calculating the MMSE matrix and then quantizing. So let's do it right. So let's do the right approach. And the way we're doing it is we would like to find an equalization matrix that is quantized and that is actually the best equalization matrix. And to do that, we would like to find equalization matrices that have structure that later allow us to build efficient hardware when we do the spatial equalization. And we call the structure of such a matrix a finite alphabet matrix. And the finite alphabet matrix consists of two components, a matrix X, which consists of low resolution entries, for example, 1 bit for I and 1 bit for Q, or for real and imaginary parts. And then also a diagonal matrix, which basically just scales the rows of this matrix to a certain value. So this is a matrix, a structured matrix that has first low resolution entries and then just the scaling of each individual output. And if you would implement that, you would have basically low resolution multiplies first with your receive vector and then followed by post multiplication scaling. So if you look at one user equipment, so you take the received vector at one time slot, you would multiply it first with one row of this matrix V. And since this row has, for example, only binary entries, then this could just be with like adders and subtractors. And then after this inner product, we do a high resolution multiplication, for example, with 10 bits. So you can see here, the hard work is done with low resolution, and then we scale it up with a higher precision method. And this can clearly reduce power consumption and complexity because most of the operations are now done at low resolution and only few operations are done with higher resolution in this case. So let's see how we can do that. So basically what we would like to do is I would like to find the components of this finite resolution or finite alphabet matrix beta, so the diagonal post-scaling values in the matrix that minimize the MSE. So basically we're trying to design a linear MMSE that has exactly this structure that makes sure that what we estimate, that our estimate is as close as possible to what we would like the users to see. And this is a minimization problem in these two values, in the scaling values and also in the low resolution values here. And this problem can be formulated per user. So this boils down to a per user problem, which is shown here. Again, the details are not particularly important. But then what is interesting, this problem can be split into two independent parts, where you first solve basically for X. And as soon as you know X, you can calculate the corresponding scaling factor. So this is interesting. This is equivalent. So this problem, these two problems I'm showing here at the bottom are exactly equivalent to showing this one. But it basically boils down that we can first find the low resolution weights. And then as soon as we know them, we can figure out what would be the best scaling factor. The problem is, even though we have this separation of optimization problems, the first step here, the step here on the left, is an NP-hard. It's a fractional program with discrete inputs. And so basically, since it's NP-hard, you can more or less do, with the current state of research, you can do an exhaustive search. And again, if you have a 256 receive antennas and you would like to do find 1-bit weights, then this would require 10 to the 154 objective function evaluations, and this is impossible to do in practice. So the question is, can we somehow do this in practice? But let's first see what is the benefit of doing this very complicated approach, comparison to just taking the linear MMSE matrix and quantizing the entries. This one here is the linear MMSE with infinite precision weights. This is at 15 dB SNR. So what you can see here is the effect of the noise. It is a fairly small system. And you can imagine, again, we only use B equals to 8, so 8 base station antennas, because we would like to do an exhaustive search. If we just take the LMMSE matrix and we quantize it, which is called FL MMSE, you basically get a pretty big mess of the receive constellation with a very high EVM. But if we solve this finite alphabet MMSE equalization problem I was showing before, we almost get the same performance with an infinite precision LMSE. So you can see by actually solving the problem that we were developing, so you actually find the weights in a principled manner, you can get significant EVM improvement. You can see you can halve the EVM here in percent compared to the simple approach that I was mentioning before. So the question is, now we know that it helps a lot to solve the principled method, but the other question is, how do we do that? So we somehow need fast algorithms to do this. And there's some interesting technique which reach back to Dinkelbach. It's like a very old optimization techniques where you can take a fractional program and you can divide the fraction into two components. So we can use this technique. Again, I wouldn't have the time to go over the details, but basically you can approximate it where you have gamma here. So you see this gamma parameter at this side, which would be the value of the optimal objective. And this is equivalent. So this problem, this optimization problem, is equivalent. And then what you can do is, assuming that you know gamma, of course, we do not know the optimal objective value, but assume it for now, then we can solve it by computing a gradient step and then a projection on the relaxed constellation set. So basically, instead of using the binary set of values, we make a convexification of the binary values. So basically the convex hull around it. And then we can use forward-backward splitting by computing the gradient, projecting onto the convex hull, and repeating the step for a few iterations, like 10 iterations max. The issue with this approach is you have certain parameters. You need to know the step size because you do gradient descent, and you need to know the optimal objective value, of course, which we do not know. But fortunately, we can use machine learning techniques, and a technique that is very widely and very popular recently, which is known as deep unfolding. So you take this iterative algorithm, you unfold the algorithm structure for, say, 10 iterations. And as you can also see here, it's basically a linear operation followed by a nonlinear operation. So this unfolded algorithm has the structure of a neural network, but where the only unknowns in this neural network are the step sizes and this optimal objective value, which we do not know. So we basically have a neural network-like structure where within each of these blocks, we really just have an affine transform. And then what we need to find is these step sizes in every iteration and this lambda value. And the good thing is we can just take any deep learning framework of your choice. We can create many, many channel realizations for whatever benchmark scenario you're interested. And then we can learn these parameters for every iteration. So we don't have to manually find a way of picking these algorithms. We can use deep learning tools. We can use them offline to offline compute what these parameters are. Then we can plug them in, and then we have an algorithm that has the best step sizes for this approach. And it turns out, for example, for this finite alphabet MMSE equalization, you can actually reduce the number of iterations by roughly 2 with the same performance. Or you could also, for example, keep the number of iterations, you can improve the performance. But the way we did it, we basically, instead of 10 iterations, we only need now 5 iterations of this algorithm and get the same performance as with a 10 iteration version where we manually picked the step sizes. So this is one of the few cases where we can use machine learning to, for example, tune algorithm parameters in a very practical way. So now the question is, probably you're asking, so how well does that work? So this is again what I've shown before. We have the infinite resolution performance with black, and we have the 1-bit performance where we just take the LMMSE receiver and we quantize. And if we solve this fame problem using deep unfolding, you can see for 1-bit weights, we get a significant improvement of about 2 dB. If we go to 2-bit values in our equalization matrix, again, we can improve the performance for both methods, for both of these methods. And then if we use 3-bit, and this is actually interesting, if you use 3-bit, you can actually really just take the LMMSE matrix and quantize the entries. You can see it's doing the same. So this method I was showing, the nonlinear method, is particularly useful if you go to really low resolution. But if you go to, say, 3 bits, you're fine by just calculating the LMSE matrix and then later quantizing. And also, what I have not shown is how we can deal with higher order, with higher precision, all these things, but all these methods can be done in practice. So now, one more last thing that I would like to talk about is that by reducing the resolution, we are not just simplifying multiplication, but we can now use completely different hardware architectures if we use low resolution inputs from the ADCs and also low resolution weights. And to explain this, I would like to show you how traditional hardware accelerators would implement a matrix vector multiplication. Typically, what you would have to, you would have memories that store the weights that you would, for example, have in your LMMSE matrix. And then you have the received data, and this received data goes to an array of processing elements, and each processing element, for example, does a multiply and accumulate operation, and then until you get the data output. So this is a traditional memory-based and processing element-based hardware architecture. And the issue with this is there is a huge amount of data movement. So data has to go from memories into the processing elements, and the data movement itself can actually be dominant or at least consume like half of the power consumption of an accelerator like that does a simple matrix vector operation. But if we have very low resolution, so imagine we have about, say, 3 bits coming from the ADCs, and we have about 3 bits for the weights, you can build something which is known as in-memory processing or processing in memory or through memory processing, where you put the weights, the memory right next to the processing elements, and the processing elements are very simple and the memories are very small. And then the data will just basically flow through this architecture, and there's no data, there's no movement from the memories, from the weights stay. The only data movement is your received vector that will go through this array in this case. And you can do this in many ways. People have proposed analog solutions. We have proposed a fully digital solution, which is extremely easy to implement. We call it PPAC, which stands for Parallel Processing in Associate Content Addressable Memory. It's a pretty long name for an accelerator. And basically what this can do is it can accelerate tasks like this and has basically no movement of the matrix coefficients in this case here. And here I can show you basically based on power simulations that we have conducted using these architectures, how much this helps. So the gray on the left side, we have area, how big the implementation would be. On the right side, we have power consumption. And this is these are results for a 256 base station case where we assume we have 16 users. We assume 16 gigahertz of bandwidth and the 28 nanometer CMOS technology. And if we would do a naive implementation, we would get 27 square millimeters of area to do this equalization task, and about 21 watts of power. And now if we use FAME, so we use finite alphabet MMS equalization, so we go from 10-bit to 3-bit without losing much in error rate, we can already about reduce by a little bit more than a factor of 2 the area. So this is really this coming from reducing the resolution of the weights of the matrix. And then if we use our PPAC or in-memory processor, you can see we only get moderate gains, but again, we get slight improvements in this case for the 3-bit case. But if you look at the power consumption here shows that if you go from the traditional naive implementation to a 3-bit FAME implementation, we reduce the power not by that much. But then if we switch to this in-memory processing architecture, we can basically reduce it by about 1/3 from the original. So you can see by not just reducing the bits itself helps to reduce power, but also by changing completely the way you're doing the processing in digital, in hardware, significantly reduces in power savings. This is now for 3-bit weights. If you can also go to the extreme case of, say, 1-bit weights, and then you will get about 9x area reduction and about 9x in power reduction. This is not shown here, but this is literally what you could get if you would be fine with the error rate performance of 1-bit weights in your equalization matrix. Okay, so now I've basically shown uplink, downlink, and also the processing, how we can reduce. Now, of course, it would be interesting to put all these things together. And we have done this. So we have looked at an architecture where we use low resolution ADCs and we use low resolution equalization. And we would like to see what can we do. And the key observation here is that this optimal resolution of ADCs and equalizer resolution depends on how many users are actually active at the given instant in time. And you can imagine there's not always all the users active. In many cases, there may be only one user. One user also depends on the modulation scheme and the channel conditions. So you would like to, in an ideal architecture, you would like to have ways of adapting the ADC resolution and equalizer resolution instantaneously to the system conditions to minimize power consumption. So this is really the idea what you can do now. With this. And to evaluate such an idea, so such a resolution adaptive architecture, what we do is we model the power consumption of the ADCs, which depends on the number of bits, the sampling rate, the number of base station antennas, and also the equalization power depends on the number of bits of the weights, on the rate of how fast we have to do the equalization, and the number of base station antennas and the number of users. And we would like to adapt all these parameters to the instantaneous system conditions. And you can do that. So here's a result. Basically, you see here the SNR loss at 1% bit error rate. So what we do is we just look at 1% bit error rate and we see how big is the loss compared to an infinite resolution scenario. And here we have this combined power of ADC and equalizer. And each of these curves correspond to different scenarios. The top curve corresponds to the case where 64 users are present in the system. So this is a 256 antenna system. And the lowest curve here corresponds to the case where we have only one user active in the system. And you can see here, for example, for one user on the left, we start basically at the case where the power is very high, but we can basically reduce the power by 1 order of magnitude or even more without losing any performance. So clearly, the case where only one user is transmitting, we can significantly reduce resolution and hence significantly reduce the power consumption in this case. This can also be visualized in the following way here. This is just a section cut. Here where we say we don't want to lose more than 1 dB, 0.1 dB compared to the 0 dB point. And you can see here the power consumption compared given the number of user equipment. So here we're only adapting it to the number of user equipments. And you can see for one user, we basically get significant power reductions. The red curve here is a baseline implementation that for one user is also only doing a multiplication with 1 row of the equalization matrix. And you can see here, the power savings are extreme. You have something that is higher than say 60 watts if you have a lot of users present in one case, but if at a certain instant in time only very few users at a time, you can go in the sub-watt regime. So this is clearly the goal of a base station architecture, that you have the capabilities of being completely adaptive with the resolution. So just building it for a fixed resolution is not the answer, but making it adaptive is the way to go here. And you can really see that there's significant savings by using this approach. And this is not just an idea we had, we've actually implemented this. So this is an ASIC that we've developed. So the ASIC is here in the middle. This is in a package. This is 8 square millimeters. It's 4x2 in 65 CMOS. It's not the latest and greatest technology, but the reason why we picked this technology is because we get a lot of pins. So this is a pin limited design. And this design supports 32 base station antennas and up to 16 user equipments. And it includes also programmable ADCs. So we can program the ADC resolution. And we use successive approximation register ADCs. And then we have also programmable resolution of the equalizer. So the numbers that you've shown on the previous slides are actually for this implementation here. And this design reaches the highest throughput of reported design of equalizer, so roughly or slightly below 10 gigabits per second. And the energy efficiency is also record. It's it's like 2x or more better than the next best design that has been reported in the literature. This is just to show that you can combine all these techniques into one chip, and you can leverage significant power savings compared to naive implementations and outperform everything else that has been reported in the open literature so far. So with this, I would like to conclude. I hope I didn't take too long. So if you would just naively take techniques for small scale MIMO and you will scale it up, it would result in excessive system costs and power consumption. So this is clearly not the way to go. But we have shown that you can reduce the resolution in the uplink and the downlink and also in the processing, and it will still work. And then you can also analyze what we're doing. Even though quantization is a nonlinear operation, you can use Buskam's theorem to do a pretty accurate analysis. And then also what we've shown is like 4 to 6 bits is sufficient. This a little bit depends on power control and so forth, but this is typically a good safe bet. And equalization with 3-bit is also sufficient in most cases. And then also this concept of having receivers and transmitters that are resolution adaptive. So depending on how hard the equalization problem is, for example, you can adapt the complexity and power of your task. And everything I've shown can be implemented in hardware. So it's not just MATLAB simulations, it's a model. So everything we've shown here, we have implemented and verified. So these things really work in practice. With this, I would like to conclude and of course, thank my collaborators. My 2 PhD students were basically involved in the FAME task and also the hardware implementations. Then with our collaborators from Chalmers, Sven Jakobsson is now at Ericsson, used to be at Chalmers, and also with Tom Goldstein from University of Maryland. And if you would like to get more information, please visit our website. And of course, I would also like to thank my sponsors. But now I'm done with my talk and very happy to answer some of your questions. And I've seen the chat is almost full, so I'm going to quickly go through this.
Yeah. So okay. So maybe I can help Marius in handling this Q&A session. So since Marius is having some noise problem at his site, so I'll take over. Actually, the first question comes from Benedict. So I mean, of course, thanks Christoph for this very impressive, very informative talk. So the first question is about the quantized design, and would it be possible to take the optimization of the quantizer itself into account, some kind of like task-based quantizations? So what's your take on it?
So you're okay. So we've tried non-uniform quantizer, and the gain is not worth it. It's also harder to implement in practice, especially if you build, for example, a SAR ADC. And so in terms of the array performance or also spectral efficiency, adapting it is not really help in our case. And especially it doesn't really help in millimeter wave where the received signals are fairly uniform. And also, as I said, like from a hardware implementation perspective, you would rather not do non-uniform quantization. I think it makes an interesting research problem, but it has probably too many practical issues to do. And also this task-based quantization could be interesting if you're, for example, not interested in estimating the user data, but for example, if you only were interested in estimating, say, how many users are there, or is it a difficult equalization problem, then I think task-based approaches could be good. But if you really have to receive the data and everything, I would go with uniform quantizers and just play with the resolution. Yeah, that's already difficult enough, and also seems to be almost best from what we've seen.
Yeah, I guess so. So the next question is from Wolf. So he or she said that so you achieve good gains at the high SNR regime for the uncoded bit error rate. But now in practice, actually, there's some forward error correction coding, and most of the cases, the system operates as a low SNR region. So like, what's the significant difference? So, and particularly from the simulations that you're presenting.
I mean, this is a very good question. I mean, this is already coded. Just that you know that then you can see encoded error rate is already a big gap. But if you, for example, go to a result that was uncoded, I agree. Let's see where I can have this.
I think he's referring to the low SNR regime.
Yeah. So here in the low SNR, I mean, the coded case would not operate in the low SNR because the error rate would be too high. But this one here is an uncoded. And yes, I agree. If you go really to low SNR here, if you would like to operate at -5 dB SNR, for example, the gaps are indeed not that significant. The problem is it's very hard to operate in these regimes because of not this case, but time synchronization, carrier frequency offset estimation, all sorts of secondary effects make it really difficult to operate here. Of course, but this is an observation that we know for a long time, that if you go to basically the lowest SNR, or like zero SNR, not 0 dB, but 0 SNR, then, for example, MRC would be optimal. I agree. If you can somehow get your synchronization and system to work, and if you're happy with low data rate, I agree. Then all these methods do not particularly help. That's a very good point. Yeah.
Okay, thanks. So the next question is on how much data is required for the learning in the deep unfolding approach.
Okay, yeah, this is a really good question. So the good thing is there are only very few parameters. You see in this case, the number of parameters we would like to learn are 2 parameters per iteration. If you use 5 iterations, we have 10 parameters. So you can imagine you don't need that much training. It's not a dense neural network where you have to set millions of parameters. You only need about 10 parameters. You don't need that much data, but you would like to use a lot of data because you would like to cover as many different channel realizations to get actually a robust set of parameters. So typically what we do is about 1,000 different channel realizations. And of course, it's not clear to us whether that's enough or not. Maybe for a company that would not be enough, but it's not really a problem of you can actually train it with few, but you would like to use many channel realizations to just make the system robust. You don't want to pick a configuration of parameters that works in like 99% of the cases, but fails completely in 1% of the cases. So that's why you probably want to really have a large data set, a representative data set. Yeah.
I see. So regarding the power, so the next question is, so regarding the power efficiency of the base stations, what's your opinion on like an all digital transmitting architecture, like the outfacing polars and that kind of stuff? Now with these architectures, DAC can be replaced with something like codec and digital PA can be employed. So what's your opinions on this?
So we have not worked with outphasing PAs and also not with polar PAs. So it's very hard for me to give any answer. I think this is interesting. Especially outphasing could be extremely interesting because in many cases you create like 2 outputs instead of 1, and then you feed 2 individual components. This is very interesting. I have not seen results on this, and I think it could be an interesting research problem, but honestly, I do not know. I mean, also in terms of algorithms, how you create an algorithm that creates a signal, for example, for an outphasing PA would be very interesting to look into, but I honestly cannot answer this question. Yeah.
So next question is, so first thanks for the nice talk. So can you comment on the modulation schemes, especially in the 1-bit case, like whether you do a PSK or QAM? And how about the new modulation schemes like those faster than Nyquist signaling?
Okay, so if you do 1-bit things, actually PSK modulation helps a lot because you completely lose any sense of scale. But there's still ways of dealing with QAM. So if you have some reference point, you can still receive QAM. But there is some trade-off. Clearly, of course, you don't want to have a too dense PSK constellation as well, because also your phase resolution is not that great. So this we have not really done a systematic study, but we have done 8 PSK and QAM and also 16 QAM and 16 PSK. And it turns out that if you really go to low resolution, it's about a wash. So basically, it doesn't really matter whether it's 16 QAM or 16 PSK. But I think to really give a definite answer, one then has to look at many more aspects like synchronization and other effects, like especially hardware impairments to see, because it could be that, for example, the QAM is even more susceptible to, especially the outer points in the constellation, to phase rotation. So I think this is a complex question to answer. But yeah, we have seen that in some cases, constant modulus constellations can actually help. In terms of faster than Nyquist, I do not have any published results. We have a student looking into this. This is a very good question. And I think I also have not seen many people really looking into this. Yeah. And I cannot really comment on results yet because it's half-baked and not ready, but this is clearly an interesting point. Yeah.
So thanks. So the next question is, so for a wideband system, if you consider an OFDM system, so is the quantization done in the frequency domain, or is it the delay domain signals in the system model?
Oh, okay. So for OFDM, clearly the received signal is quantized, and that's in the time domain. But for example, the low resolution processing is in the frequency domain, and there the weights are quantized in the frequency domain. Yeah, so that's how this works. Yeah.
I see. So the next question is from Marius. So do you also consider quantized channel state information in your performance evaluations?
So this is a good question. So typically the channel estimates or the pilot signals are received anyway through your ADCs. So the received pilots are already quantized, but we have not looked in the case of what happens if we intentionally reduce the resolution of the channel estimation task. And I think this question kind of goes into this direction. So we have not looked into this, but since we already know that 3 or 4 bits is enough, this also applies to getting channel estimates at 3 and 4 bits. But we have not really seen what would happen if you intentionally say, let's make our channel estimates lower resolution as well, like lower than the 4 or 3 bits that you will get. Yeah, so this is a good question. And we have not really looked into this. This is a probably interesting project to see what happens in that case.
Yeah, I can see there's a lot of open problems that can be solved. So so next question is, can you also comment on the message parsing algorithms like GAM in the few bits uplink, and in the downlink, how do you think about the precoding using message parsing? Okay,
so GAMP is really good if you have rarely fading channel matrices, which of course you never have in practice. You basically get ML or map performance. If you have, say, millimeter wave channels that are extremely structured with nasty correlation properties between users, these methods tend to fail completely unless you start doing tricks like damping and tuning with neural networks. So I would say they're really good methods, also for quantized systems, but you have to make sure that they also work in reality with really annoying, with annoying channels. Yeah. In the downlink, I have not seen much results using message passing. There's one result that analyzes with statistical methods the downlink, but I have not seen a corresponding message passing based algorithm. So this is interesting. Maybe there is something recently, but I'm not aware of any results about that in the downlink. Yeah.
Mm-hmm. So next question is, have you considered about using the method of reductions, the errors of digital measurements through random modulations? So I guess it's a question about random modulation.
Yeah, my guess is that this goes towards the idea of dithering. Like you could take not just the fixed quantizer. I'm not sure. I'm just guessing. Yes, you could dither. You could like. There's multiple ways actually. There's some interesting. Let me get the system model already here. Let's see where I can find this with too many slides. Okay. So what you could do is one approach is you could add a dithering signal. And then ideally, you could potentially get better performance. The problem is to create the dithering signal, you now need the DAC, and the DAC need to be high resolution, so everything you do is completely lost. But what you can do is you can make your ADCs to intentionally have slight mismatches. So say ADC 1 has a slight offset, ADC 2 has a slight offset, and this can help a little bit, but it's not really significant. And you would have these mismatches anyway in practice if you build an ADC. So, but these methods help a little bit, but they're kind of underwhelming how much the impact is. So it's not something that you would intentionally do it doesn't really help. Yeah.
I see. So I hope that this answered the audience questions. So the last one that I saw here is so the following. So for broadband system, like can you change the order of beamforming and channel noises to get additional speed ups and also to reduce the hardware?
I don't fully understand the question. I don't understand the part order of beamforming and channelizer.
So maybe he's asking about what if we change the channel equalizer? Maybe.
Yeah, I do not know. Maybe there's a way of clarifying. Of course, the person who asked can also send me an email. So I do not know. Trying to think what you could do here or what the question is about. Gain additional speed ups to reduce hardware.
Neither.
I honestly, I'm sorry, I do not fully get it. But if the person who wrote this question can just like send me an email, maybe with more details, I'm very happy to answer it. But I do not.
All right. So know. Maybe in the meantime, let me ask the audience. So if you have further questions, like please, like, and this is your last chance to ask Christoph. Or if you have further questions, you can email him.
Yeah, and, just go to the website if you forget about my email address, or just it's my last name at eth.ch. That's the email. Yeah, feel free to ask any questions. I can also send copies of the slides if people want.
Right. Yep. So I guess that's it. So I guess thanks, Christoph, for this very nice talk, and I mean we know we learned a lot. So thanks a lot.
Thank you very much for having me. Okay.
All right, so thank you all for attending this one-round signal processing seminar series. So this is actually our third last talk in the fall season, as I recall. And also next week we're gonna have a talk on our seminar on the Wednesday again, not Tuesday. So hope to see you all next week again.